Good morning, everyone, and welcome to the Wolverine Caucus. We like to think that we're changing the world one forum at a time. And these forums are brought to you by the University of Michigan Office of the Vice President for Government Relations, the Alumni Association, and we are proud to be able to bring some of the most illustrious speakers, researchers, and experts from the University of Michigan here to share with you. So today we have an amazing topic, autonomous vehicles, things that live for us so we just sit there, and one day cars that will drive us. And so without further ado, I would like to introduce you to John Kinsey, who is the Assistant Vice President for Research at the University of Michigan. And John helps to connect all of the research and collaboration between the three University of Michigan campuses and with industry and government. And he then will introduce our speakers for today. We're glad that we were joined today by Representative Clementi as well as Representative Colby Wright. Without further ado, John Kinsey.
Hi, and good afternoon, everyone. I'm the Assistant Vice President for Research at the University of Michigan, and I'm going to be very brief. Actually, this is just-in-time technology. Had I had an autonomous vehicle, perhaps I would have gotten here a little sooner, but traffic, I walked in the doors moments ago. So just setting a little bit of context for everybody here. We hear the word autonomous vehicles, and most of us think about cars. That's the obvious thing to think about, but autonomous vehicles are and will be very pervasive in our lives, in the air, on the water, under the water, in space, pretty much any place we think about where vehicles operate. So I'd like to set the tone that when we think about autonomous or uncrewed vehicles, we're not necessarily at the University of Michigan and great research partners like Michigan State and Wayne State thinking about it as roadway vehicles. So you can hear a lot about that today, particularly in the air. Also, the autonomous vehicle framework is a bit of a new place for the universities in that we are now, our research and our educational tools are, in more ways than ever before, purposefully leaving the confined laboratory spaces of the university and interacting with the public and learning together with the public about how these new technologies will improve, change, and impact our lives. And as partners in the legislature, it's very important for all of us to think about these things together, how the good and the bad, and some of what you hear about today. And your role as our partners and our role as your partners is really harkens back a long time ago as to how originally the universities were created, were a place of learning and thinking, and the land-grant colleges were created by the federal system so that we can have this new framework about how we will, again, together create a regulatory and a legislative environment where we can advance safely and thoughtfully the research and education, and eventually widespread commercialization and adoption of these tools. So I think that's what we're hoping. We work together on that. We have some great speakers who are absolutely world experts in this regard with their technologies, and policy leaders and thought leaders for the country as a whole. So we're very proud to have them here today. I think there is a point of acknowledgement that I just want to make clear up front that sometimes the views on these things are wide-ranging. We all have different thoughts on how these things should work and how they should work together. And universities, I can probably say with confidence, our colleagues from Michigan State, ourselves, all the way from Stanford to MIT and everywhere in between, are still struggling ourselves with how we are going to accept, encourage, and cultivate these things on and off campus. So there's a lot of different points of view. We're working together. We hope to share with some of those today. So without further ado and without a long introduction that will take away from the content, I'm going to let the speakers introduce themselves. So please enjoy this, ask a lot of questions, and I'm looking forward to the wide range of viewpoints of this once we finish today. Thank you.
So, good afternoon officially, everyone. It's my pleasure to be here speaking to you all. I am not Edwin Olson. My name is Steve Bozar. I am a research fellow in computer science and engineering at the University of Michigan, and I have a PhD in mechanical engineering from the University of Michigan. I've worked with Ed on this project for about a year, and it's a great pleasure to be speaking on his behalf. In case you want to know what Ed looks like, he's in the middle of this photo. Somehow he got right front and center. And his hair may or may not be significantly grayer than that, I'm not sure. But I believe this will probably be the source of my gray hair as well. Just as a quick introduction of the timeline is, our group's participation in autonomous vehicles. So in 2007, Ed worked on the DARPA Urban Grand Challenge, which is an autonomous vehicle competition. And then in the subsequent years, as he says, the funding sort of dried up a little bit for autonomous vehicles in the wake of that competition. So he switched to a smaller platform of these magic robots. So he worked on sort of autonomous groups of robots working together. But then in 2011, he came back to autonomous vehicles. So this is a Ford Escape that was outfitted with autonomous sensors and behaviors by graduate students, and by 2014 we were working in a full partnership with Ford to get their autonomous vehicle program running. So that's a 2014 Ford Fusion. It's this platform that we had at the University of Michigan, and it also is the same platform that Ford is using. And as of 2016, Ed is now running the localization and mapping portion of the Toyota Research Institute that's just opening in Ann Arbor. So the big question, why autonomous vehicles? And the answer really is for safety. So there's about 30,000 fatalities a year in the US, over 1 million worldwide, and there's significant economic and social impacts in the US. So on average about $900 per person per year. And a big reason that we have crashes is because of humans. So humans speed, they get distracted, they drink and drive, and autonomous vehicles do none of these things. Hopefully. I don't program to do that, so I think we're okay. And there's a lot of other reasons as well. Besides the safety and economic benefit, there's a whole world that can be unlocked by having mobility for different people who weren't able to have that before. So blind people or the elderly who are unable to drive themselves, it enables them to have mobility to do daily tasks. It also lets us use roadways more efficiently. So 2-lane roads can become 3-lane roads, 2-way roads can become selectively 1-way roads if we have the algorithms in place to do that safely. Autonomous vehicles can also more efficiently use they have better energy efficiency, they can be programmed to drive more energy efficiently than humans, and they can reduce manpower requirements, so you can take humans out of sort of dangerous tasks. And so one key point here is that these other reasons also have economic value that may offset a safety risk or may just add to the value that may be harder to calculate directly right now. So moving sort of over to the technical side, I would say that the workhorse sensor that almost everyone uses on an autonomous vehicle is going to be a LiDAR sensor. And we, on the Ford project, use 4 Velodyne sensors. And how these work is they send a pulse of light out into the world. They wait for it to reflect off of something, and the time that it takes for that time of flight gives information about how far away that one point is. And we do this 2.5 million times a second over 4 sensors, and we're able to build up a really big, really detailed model of the world. And the reason we use 4 Velodyne sensors instead of some companies like Google use 1 right at the top of their car is it gives us greater control of the beam pattern. So if you ever see a cross-hatched pattern, like you see on this picture, you're going to know it's one of the Ford vehicles. And so what can we do with this sensor? We can build really detailed high-fidelity maps of our environment. So this was a map that is completely 3D reconstructed of, obviously, Michigan Stadium. It will transition to downtown Ann Arbor, and what we can do is we can build up these maps ahead of time. And then when we redrive in these places, we're able to localize, we would figure out where the vehicle is within centimeters. So the vehicle knows exactly where it is by just comparing the prior map to its current sensor readings. So humans don't actually do that. I don't need to know where I am within centimeters. I have a good idea where I am laterally within a lane, but longitudinally I don't really need to know within that sort of accuracy. So the reason we need to do this with autonomous vehicles is because it is currently beyond the state of the art to be able to decode roads reliably in real time. So we can decode them, it is possible, it's not beyond what we can do, but the reliability really isn't there to have them testing on public roads. So what we do is we cheat a little bit and we say, let's gather all the information we can ahead of time, process the data, and then we can localize within the map and we can sort of annotate that map and know what is the road, what is the sidewalk, what are these portions of the road that we should know about. And so the car doesn't have to figure it out. But in that paradigm, the car does need to know exactly where it is. It does matter laterally and longitudinally within centimeters where it is. So we are able to do that, and that is the current state that we're working off of. So a quick poll. If I wanted my autonomous vehicle to match human performance, what do you think this number would be? One fatality per how many miles driven? What do you think is the average in the United States? Anyone?
300,000.
300,000. Okay, anyone else?
A million.
A million? A million, okay. It's actually 100 million miles. So, it's okay. This was not a graded test. Everyone really underestimates what this is. So that's a staggering number. So there are a lot of vehicle fatalities in the United States, but that is a testament to just how many miles we actually drive. And just to give you some context, I mean, there's 209 round trips to the moon. I think Google's logged some more hours since the slide was made, but it's 2 orders of magnitude higher than the number of logged miles that Google has made. So you would not expect Google's car, even if it was matching a human right now, to have be involved in any fatalities. So it's in addition, Google is, when they're doing this testing, they have an undisclosed number of human interventions. So we don't know how much, like what circumstances would have caused maybe a fatality if not a human had intervened. So it is very, very difficult to even test whether these vehicles are going to be up to human standards. So not only that, so that's a very large number, one fatality per 100 million miles, and that bar is just increasing. So because we are in parallel working on advanced driver assistance technologies like electronic stability control and steerable headlights and collision warnings, I mean, it is not unfathomable that we could reach human driver performance of being better than one fatality per billion miles. So the humans are just getting better, and it is competition to see who's going to end up as the safer driver. So the question is, can we ever even catch human performance, given that we have these other safety systems in the loop? This is a video, maybe you have seen it before. It became very famous maybe 2 months ago. This is a Google vehicle in its first at-fault crash. And I'm showing this video just to illustrate that this is a very complex situation. So the Google vehicle was stopped for some sandbags in the road. And the road actually was a very wide road. It wanted to turn right, but the bus was already in the same lane. And so what happened was there was confusion as to who had the right of way when the vehicle wanted to make a right turn but couldn't do it as tightly as it wanted to. So this is a very complicated situation that I could see myself getting into with that bus, and it's telling that this is a very, very complicated system that, this particular situation may never happen again. So we really need to be able to pin down why these things are safe and be sure that we can handle these sort of very uncertain scenarios. And the reason that it's so difficult is because they're very complex systems. So this slide just shows the number of lines of code in various types of vehicles, and the top line is an average luxury automobile. It's not an autonomous vehicle. So any autonomous code is going to have to be on top of that, and compare that to the lines of code at the very bottom that's in the F-22 Raptor jet. I mean, it's much, much more, and you're only going to add more and others. So the system's getting more and more complex. So now that I say they need to be safe and we need to figure out, we need to match human performance, there is is there safe enough? Is there a number that we are trying to hit? What is that number? And so I brought up two numbers here. So 658 fatalities per year, that would put autonomous vehicles on par with driving one fatality per 5 billion miles. And that's the same as the number of people that die of heat stroke every year. If we were to reduce it to 50, that'd be one fatality per 64 billion miles. That's the number of people that are hit by lightning every year. So I'm not sure that we can ever reduce it down to zero. The goal is not zero fatalities. The goal is to get it better than human performance and to be able to quantify how good our performance is going to be. And it maybe sounds a little crass if you are not into, if you're not familiar with these terms, but there are economics of moral danger. And so this idea of a micromort is a micromort is a 1 in a million chance of probability of dying from a certain activity. And depending on who you ask, reducing one micromort is worth between $6 and $50. So currently car death stands at 73 micromorts per year. So you can see that maybe not as an individual, but as a society, we are sort of valuing a budget of $430 to $3,500 per year to improve car safety. And this is a little thought experiment. It sounds a little strange. So if we consider sort of some bar where we're safe enough, so on the y-axis here, I know it's math, I'm sorry, and then the y-axis here we have a log scale of deaths per year. You can see that maybe we decide that there's some safe enough bar, and humans, as we improve our advanced safety systems, are getting better and better and better. And maybe full autonomy over time may catch human driving, maybe a long way out before we can catch it. But let's think about perhaps maybe that bar of safe enough actually increases based on the other societal benefits that happen as a result of fully autonomous vehicles. So there are economic benefits associated with having an autonomous vehicle that you don't have to drive, that is more energy efficient, that allows people to do other work while they're commuting, things like that. So I don't see this safe enough bar being raised to the same order that it shows on the graph, but this is an interesting question, thought experiment of, are we willing to give up some amount of safety for the increased economic benefit of having fully autonomous vehicles? So another question that sort of arises from this is somewhere in between advanced safety and fully autonomous vehicles, there's maybe like a mostly autonomous vehicle. And that's a vehicle where, you know, it most of the time does driving just fine, but when it needs your help, it sort of chirps at you and says, hey, I need some help. I'd put this slide in. It's from an MTV show with a name that I won't say in this forum, but it's sort of akin to dressing up like a zebra and waiting for a lion to attack you. It's a bad idea. It's what his point is. It's a bad idea. Do not do this. Okay, why? Why should we not do this? Okay, it's a human factors issue. Humans cannot be trusted to intervene at the time when they need to. So if we look at this sort of spectrum or this continuity between mean time between interventions, so currently, the state of the art, we have cruise control, lane keep assist. You can take your hands off the wheel, you can take your hands off the pedals for seconds at a time, but you're still engaged in driving. At the other end, you have complete, total, full autonomy. You could put your kids in the car, you would drive them to school, no problem. No one would ever ask anyone to intervene. It's this middle part that's really hard, because when you take your focus away from driving for minutes or hours, and the car asks you to intervene 1 second, 2 seconds, even 5 seconds before it's confused, humans just are not capable of getting in the mental state necessary to make a driving decision that fast. There's many studies that have shown this. So this sort of area between where we're currently at and full autonomy is a no man's land. We think this is a very, very bad idea to implement and give to consumers. And it's even worse than that, because if you are not driving your car 95% of the time, you're gonna have decreased feeling for your own car. So when you get in a rental car, the brake's a little stiffer than you're normal to and than you're used to, and it just doesn't feel quite right. And you're going to get people are going to get less practice doing these maneuvers. And what we're going to do is we're going to ask them to deal with the hardest part of driving. That doesn't make any sense. The easy part is going to be for the machine. And if the person can't handle the easy part, how are they going to handle the hard part? So it's just a bad idea to try and implement and field these systems in the real world. So given that I have strongly condemn this idea. What do we do? So no to most autonomous vehicles, but there is still room for fully autonomous vehicles. So there are posed many interesting research questions, and there's a lot of room for growth here. But in the immediate future, there is another way, and that way is to sort of keep humans artificially engaged in driving, or actually driving, and give them sort of a safety net. So they're basically bumper bowling. So the worst case scenario in bowling is where you get a gutter ball. So if you put the bumpers down, it will prevent you from getting a gutter ball. So there are systems in place. This is where we think that there's the opportunity for immediate potential to sort of prevent crashes. So where the goal would be sort of trying to make an uncrashable car. So a human is driving, but if you try to do something that will cause the car to crash, it will either not let you do it, or it will reduce the energy, reduce your speed enough that the crash will be as mitigated as possible. And so one way that we are looking at both of these research questions is by using a closed test facility called MCity. It opened last year, and we are very grateful to have it at the University of Michigan. And it is a wonderful 32-acre facility that was built for testing autonomous and connected vehicles. And what we're able to do at MCity is we're able to so I talked before about 100 million miles per fatality. So if you wanted to test that, you might want to try and put 100 million miles on it, but not all miles are created equal. And so what we're able to do at MCity is put really hard miles on those vehicles and really stretch their capabilities and put them and see what their limitations are before we ever put them out on the road. And so we're hoping that we're able to do some testing that's really hard miles, that's able to figure out how to be safer without driving all of those miles. So wrapping up here, so we see huge potential for safety and economic benefit. And I guess I want to stress that the goal is not to get to some level of autonomy. The goal is the safety, and it is the economic benefit. And if we can get to those in a piecemeal way, or if we can have one component that gets us part of the way there, then we need to pursue that. So if we can apply it to specific applications, for example, highway driving, if we can reliably drive on the highway autonomously, and that could get us towards those safety and economic benefits, then that's the kind of low-hanging fruit that we should be aiming for in the near term, with the long term being full autonomy in the future. And while these early systems might not feel autonomous, they will provide us with that economic and safety benefit. So what does this mean from a regulatory perspective? Okay, so we need to be able to allow for testing and research both in industry and academia. So while I said it's a very bad idea to have consumers in a situation where they are not ready to re-engage with the car, the risk to public safety with a trained engineer behind the wheel is minimal. So I have been a safety driver myself, and we are very well trained to pay attention even while the vehicle is performing autonomous tasks. So we need to have, so we are an engaged party, we're always engaged, we're making sure that we know what the vehicle is doing at all times, and we need to have a system that allows for those kinds of testing with trained engineers to take place on public roads and in private closed courses like MCity or the new Will Run test facility. And so we believe that Michigan should be the place for autonomous vehicle development. It makes sense. We have major OEMs here. We have outstanding research strengths in Michigan, Michigan State, Wayne State, other universities. And we have, unlike California and unlike Arizona, which is another two testbed states, we have very interesting weather and road conditions. So we have the potholes, we have the snow. This is not saying don't pave the potholes. Let's get that too. But we have those things, and so it's a really interesting place to be able to do that work. So just to finalize here, so if I have a thought experiment. So imagine I have an autonomous system that drives at 1 fatality per 100 million miles. So as a test engineer, I have driven, maybe not personally, but we have a system that has never ever seen an accident. I don't know anyone, no one I work with has seen anything that looks even remotely close to a fatality. So let's say we go ahead and field that in the real world across the board. So that would mean a catastrophic 10 times increase in road fatalities to 300,000 per year. It would be disastrous. So we really need to be careful in getting these really large numbers out there. And it's very difficult. So we want to know when a system is safe enough for commercial deployment. So the assessment that I'm trying to hammer home is that right now the technology is not ready for full autonomy, and we cannot allow humans to be on standby. It's just not feasible. But even if we disagree on where the technology stands or what should be the approach, we need to know objectively what safety means and how we're going to define safety and how we're going to evaluate it. And so I don't know the answer. This is a research question, and so we want to leverage the researchers in the state at the universities to be able to answer this question. And we think, as a general approach, to leverage MCity, to leverage these close course, hard miles kinds of things, in conjunction with simulation and validation to try and get something close to that 100 million miles. And with that, I think I have a couple minutes for questions right now. Sure.
Just sort of a factual question, and thank you for your presentation. But I think it was in maybe your second or third slide. It was the safety challenge. There was in parentheses. It said 21% by dollar.
Sure. So
what did the by dollar?
Yeah. So that let's see. Right here.
Yeah.
Okay.
Speeding 21% by dollar.
Right. So I believe. So I didn't make these slides, unfortunately. So I believe that is based on the dollar amount of the economic cost of speeding. And so I think that the percentage. This is the percentage of damages by dollar, not the percentages of deaths.
Yes, you're at your test facility, used by a lot of commercial businesses.
Absolutely.
Do they share information with the university of what they're doing, what they're learning?
So it depends on the relationship that those different companies have with the university. So some want to use it as a closed test track, and that's allowed. So they can do things on their own, and other researchers may not have any idea of what they're doing, and that's fine. There are also collaborations between university and companies. So Ford and U of M have a project together. Toyota and U of M now have a project together, and so they will collaborate on those things. So it's really whatever the company wants to do.
I have trouble with the hazard recognition. The assumption that cars are on roads. We have animals on the roads too.
Of course.
And some of these are pretty large.
Yes.
A week or so ago, I had 2 sandhill cranes standing in the middle of the road, and they kept moving one side to the other. And as I got closer, I thought, well, what are you guys going to do? And sandhill cranes are as tall as I am. I got right up, stopped, rolled the windows down, yell at them, and they didn't move. And they moved enough so I could get the car. A few minutes later, another car come the other way, and I thought, well, what's going to happen now? All of a sudden, brake lights go on. I had to do the same thing. But you get what is that's out there, and what is it going to do? A car, you can do certain algorithms on what they're likely to do, but an animal, big animal?
That's a great question. It's an ongoing research question. I will say that near MC is fenced off, but near MC there are congregations of deer that kind of wander around. So we have collected data sets where we have seen crowds of deer. And I will say that the general approach that we take for vehicles is we have a model of how they're supposed to move, as you kind of alluded to. And what we can do without writing a specific, this is a deer detector, this is a cow detector, this is a crane detector. I mean, that's not really feasible. So what we can do is we can say, this is a thing, I'm not really sure what it is, I'm going to be really careful around it. And so that sort of eliminates the need to know exactly what something is all the time. I mean, in your example, I might not have recognized what this crane was. I may have said it was a bird, but I don't know exactly what kind it is. And my behavior can be modified without knowing the exact specifics of what it is. Let's see. So
I'll just go ahead. Are there certain categories of accidents that autonomous vehicles could do better on than the current ones? Because it seems like with driver vehicles are already addressing what seems to me like the most dangerous ones, drifting out of your lane, reducing your kinetic energy when something jumps up in front of you. what are the autonomous vehicles going to do better at than what Honda sells right now, where they slam on the brakes?
Sure. I mean, so ideally, an autonomous vehicle would never get itself when you're driving, even like in a hard driving scenario. And so you're going to have some sort of property damage. You may have some sort of injury. Additionally, so I think that sort of to answer your question, just being generally safer and not getting even close to those sort of situations. There are situations where those technologies, they can warn you, they can beep at you, maybe if you're going to sideswipe someone, but they're not going to take over for someone for you if you do that.
So you don't even need to bail out the driver if you don't get too fast to bail.
Exactly.
You will. Okay.
Maybe
I think we have to.
Yeah, well, let's switch speakers and then I can take more questions at the end.
Yeah, we're not in a hurry at the end, so if you can stay an extra few minutes, we can answer all kinds of technical questions. Okay.
I think some of these questions are going to be common because I'm not going away from autonomous vehicles. I'm just going to talk about planes, which some are autonomous and some aren't. So one of the things I like to start out with is to remind people that we're not thinking just of commercial transport, where you go to the airport, go down the jetway, climb on, and then take off. And we're not just talking about the drones that have been popularized in the media that you might see your kid playing with, that we're talking about everything. Because if you go back in history over 100 years to the Wright brothers, what you see is a group that used the technology to their advantage, even 100 plus years ago, in a way that made sense. The Wright brothers flew model aircraft. And when I say model aircraft, I mean gadgets that at the time were made out of balsa wood and other materials. They needed to test the aerodynamics, they needed to test their control strategies, they needed to test their motor, their propulsion system. And if they had not done these tests, they almost certainly would have died when they first flew with one of them on board, because they found problems with their systems because of those tests. I want to remind you of that because we're now in a situation where it's very hard to do the tests that the Wright brothers did in the early 20th century. As a university researcher, as an employee of a company in the United States because of policy. So we'll circle back around to that a little bit later, but maybe that's the most important thing that I have to say in my presentation today. So if you go from the Wright brothers, pictured on the right, to what happened next, we find a proliferation of a lot of different concepts. Most of the early concepts used wings to provide lift, to hold the plane up, as long as you flew above a speed called stall speed. We still do that today because the reality is if you can provide lift with a structure that doesn't require actively powering or propelling the vehicle, you get a huge savings in terms of the amount of fuel or energy that you have to put into the aircraft. That hasn't changed today, all the way down to the bottom where you see the picture of the 787, one of the newer airplanes. What that means then is that we have a whole history of becoming more aerodynamically efficient, of developing a series of propeller-driven jets and other advanced technologies to propel the vehicle. We can go fast and we can go far because we have made really good advances in those areas. And then you see that little CNN thing on the right. We also have gotten to the point where we can micro-miniaturize the sensors, the computers, and we have pretty decent ability to store energy in small batteries. So now we're able to have things like these quadcopters and octocopters, the multicopters, that have allowed us to have a very low-cost way of people ranging from hobbyists to people that have really important missions like delivering medicines to actually get up into the sky. This has caused challenges in many ways. Right, so who flies right now? Well, the first and foremost flyer is the passenger on what I'll call a tin can with wings. Right, there's the traditional fuselage that holds most of the people and the payload, and then supporting all of that are the wings, the engines, and the control surfaces and tail to stabilize the vehicle. Well, hidden in this is a vast number of sensors, computers, networking components, and software. In terms of number of lines of code, you quoted the F-22 lines. Certainly the F-35 has had a lot more and some pain to go with that, but the 787 and the A380 have a comparable number of lines to what the car has. So there's a lot of people out there that are trying to write and debug and integrate code, whether it's for cars or airplanes, and that continues to be one of the most costly elements of developing a new vehicle, whether it's an aircraft or a car. Well, so I want to say now, this is a talk on autonomy, and here's what nice airplane. I love flying, right? So I'm going to show airplane pictures. It's something that we do. But I also want to remind you that there are still people out there flying the Piper Cubs, like the little yellow thing in the middle. And this has caused a bit of the same problem in the skies that we have with the car on the road that's being driven by someone that has complete manual control alongside something with the LiDAR that's expecting certain behaviors. So that continues to be an issue for aerospace as well. But let me now ask the question. If you're flying on a tin can with wings, would you climb on board that airplane, certified, ready to go, if there were no human up front? I mean, how many of you would do that today? How many of you would not do that today? Right, so this is pretty typical, right? You still ask people, and the vast majority are like, I want that person up front. All right, now let me ask another question. How many of you would ride in a Google car that doesn't have a steering wheel and doesn't have a brake pedal? How many of you would not?
Depends where you're going.
Well, I mean, let's say you're going at speeds where you could not, right?
Yeah, you know.
Well, but let's say you're going freeway speeds. Freeway speeds. Well, so this is something to think about, because the reality is there are some psychological issues that enter into this. The average person is more afraid of flying than they are of driving. Well, so this is the type of thing that we have now. And in business aviation, if you were to look at safety statistics for commercial aviation, it's absolutely excellent. But that's not because, and I'm going to insult pilots right now. I'm a pilot, so I get to do that, but I apologize to any of you who are also pilots and don't like to be insulted. But let me insult myself. Pilots aren't miracle workers. They're well-trained, but someone who has driven a car for 500,000 miles, or a truck driver who does that for their living, is also well-trained. Right? And so it's not like there's magic when you climb into the cockpit that makes you suddenly better able to fly than the average, say, commercial driver with a lot of experience is on the road. That's just the way it is. So, I'm going to go here. No, let me go back. So, what is, I'm going to skip a couple slides and then come back. What happens in the passenger transport? Well, there's this thing called the FMS, the Flight Management System. And it was designed to assist the pilots. Well, you know, you did a great job of leading into something that I want to quote from your presentation. Why not mostly autonomous? Well, the answer is because you then expect people to intervene when the situation is difficult, in real time, and we've just heard a presentation where experts in autonomous cars have said that's a bad idea. Guess what? Every plane flying today that has a flight management system in it is doing exactly that. That's a big deal. What that means is that the pilots in a commercial transport aircraft, fly-by-wire, joysticks, computer screens, no direct connection with the controls, today relies on the software to follow the flight plans. That software can turn off, in which case alarms sound, messages scroll down the screen, and the crew has to jump in and save the day. That was the design of the system, and it's 30 years old. One of the reasons we persist with this design is not that the engineers at Boeing are stupid. They're quite intelligent, and they work hard, and they know how to automate vehicles. In fact, they have fighter planes that have way more sophisticated autonomy than are on the commercial transport. But right now, there's no economic model for making fully autonomous commercial transport, because the people, like are sitting here in this room, want the pilots up front. And the airlines want what the people want, because they get to sell tickets. So what this means is that commercial aviation, which started out being the most autonomous, most redundant, most reliable system 30 years ago, may very well be the last autonomous vehicle that we see. I may retire before that happens. And it's not because the technology is impossible. And it's not because we're going to have increased risk if we make first class the seats with no controls that look out the window. It's because we don't trust the autonomy when flying. All right, let me get off that soapbox and back to the rest of the presentation. So, what kind of things do we do at the University of Michigan? Well, here's where I'm going to show a couple of videos and talk at the same time. Well, we use a lot of small UAS for education and research. I have no idea how loud this is going to be. Let's see, I hear there's a volume control. That noise gets annoying after a while. So I'm going to turn it down quite a lot. That's what a quadrotor sounds like. And one of the things to think about here is, this one is pretty big. It has 12-inch propellers, so what it lets us do is carry student-designed payloads, and we can have reasonable-sized computers on it, so it gives us a lot of flexibility. This is the aerospace building, FXB building atrium, and you can see tethers attached to it. So what these people are doing is testing an autonomous control system, and the tethers, I'm on the left, we're pulling them occasionally and seeing if it can go back to where it started, and this one is working reasonably well. A little bit of altitude oscillations. But how we converged on this test environment is because we can't fly outside, right? Because we are a research institution, and furthermore, there have been some issues even on campus, not by university researchers, but by hobbyists doing some things that they shouldn't, which prompted the University of Michigan to issue a campus-wide ban on flight. Now, this has been declared a designated research and education space. Sorry, John, I had to say that. You knew that I was going to. That's kind of silly, isn't it? But that's the only way we get to fly there right now, even though we have ropes. Well, so this is a way that we can still expose the students in aerospace to flight control, to software for flight vehicles. We also use these platforms for our robotics graduate students to learn about kind of autonomous manipulation when the manipulator is being carried from place to place. So this past semester, I was teaching a class where we did an autonomous perching experiment, where they designed the manipulators, manufactured them, grabbed the bar autonomously, and released it.
Another question?
Yeah.
I saw a demonstration of smaller quadcopters 2 or 3 years ago at the Engineering Open House. Can't you do that anymore? Where it had 2 or 3 of them flying at the same time without tethers?
Yeah, so we could fly without tethers. There are 2 reasons to fly with tethers here. One is safety, because even if a smaller vehicle were to hit you in the face, it would still not be a good day for you. And the second thing is that we actually preserve the vehicles, because we can have a student that writes software that totally doesn't work. And we can pull the tethers on both sides, have the person turn off the whole system, and the thing doesn't crash. So it's a good idea for us just to have this kind of controlled test environment for that kind of experiment where we might have software that doesn't work.
And you can't fly outdoors.
Well, so we cannot fly outdoors, and it doesn't matter the size, for 2 reasons. One, because campus banned outdoor flight. That was the executive officers at the university. It had nothing to do with the faculty that actually wanted to fly. And the second reason is that there is an open question as to who owns the airspace and who controls it. Right? If the airspace, say right outside the aerospace engineering building, below the tree line, below the rooftop, is actually the sovereign property of the United States government, which is what the FAA is claiming, then the university has nothing to say about it. Right? That's a big deal. That's why I'm standing here right now. I like to talk about planes and autonomy and all of that, but the reason that I spend kind of a lot of time in Washington and other places is because I don't think people realize what's happening with this airspace issue right now. If you look at the FAA Reauthorization Act, there's some pretty scary stuff in it. We'll get to that in a minute. I have about 5 minutes left. So this is another video that I wanted to show a small part of. This is a student team called MFly that competes in the Society of Automotive Engineers, or SAE, heavy lift competition each year. This is their 2016 vehicle, and the goal is to fly as much as they can. One of the reasons I show this vehicle is that there is no way it would fly indoors, because it's just too big. This vehicle falls into a gray area where you have to ask the question, is this a hobby which would mean that it's protected by Congress as a vehicle that can fly under a particular advisory circular that exempts hobbyists from all the rules? Or is it actually an education and research device, in which case what they're doing right now is fine because that is approved, that's the competition itself. But when they fly locally to prepare, that's a gray area. Right? The university really hesitates to do anything to stop them because this is an incredible education experience which has been really valuable since model aircraft have existed. To have a student not just learn the math in the classroom, but to also be able to actually build and fly, to not succeed. The FAA right now wants to certify things or exempt them because of safety of the vehicle, even for things that are small like this. Well, I'll tell them right now, that vehicle is not safe. Right? Anybody who's gone to a model aircraft field knows that those vehicles crash. He was talking about 1 in 100 million hours. Right? What do you think the statistics are on a hobbyist model aircraft at a big grass field? Right? 1 in 5? Well, if you're going to have some kind of approval process that requires the vehicle itself to have some kind of operational safety statistics, and you don't pay attention to the fact that you're flying over a big grass field as opposed to people's houses, you're going to get the wrong answer. Because we don't want to stop everyone from flying just because they're not a hobbyist. If they have a vehicle like this that is student designed, student built, important for education, important for research, but it's not safe. And when I say safe, I'm using safe in quotes. It is absolutely safe operationally because they're not flying over people. They're not flying near airports. That's hobbyists who haven't been told by their faculty members that they shouldn't fly near airports. Right? This is different. And, well, this is a smooth landing. They would be upset with me if I showed one of their crash landings. So they were successful. Right? That was completely designed and built over the past 8 months by the students at the University of Michigan. And every year, a new team comes in, and they get this experience. While they're learning calculus, they're also learning to fly. And that is something that we don't want to take away. But we may.
That's a radio control.
Yeah, this is just teleoperated. They have 2 levels of this competition, so they did have an autonomous payload drop part of it. It's a new competition that they're starting up alongside this, so there'll be a little more software in the future. Right, so these are the videos that make the public want to ban drones. Right, and I can share this if anybody's interested in watching any of these, but it's very easy to find them. You go to YouTube and type for crash video, UAV, or drone, and you'll find them. Well, this is not universities. Right? This is not the people who want to do aerospace or software or robotics or autonomy research or design, build, fly. This is the people who either don't know because they have no training, they're the hobbyists, or the people like CNN or ESPN who haven't actually thought about the safety of what they're doing, but they have a compelling application, and these things are cheap, and they're easy to click buttons on a laptop and get up in the air. So we have this problem right now where we have a community that isn't too educated about the use and safety of these vehicles, and they're the ones that are going out and flying over people's heads with quadcopters. Well, a quadcopter, if it loses a motor, what happens? It tumbles and it falls wherever it happens to be. Right? There are many other reasons. The most common reason to lose a quadcopter is because of low battery energy. You get excited, you forget that you were flying for a while, the battery runs out, and then what happens? Down. Right? It doesn't have a lifting surface. When those motors fail, it goes down. Well, these are things that can be stopped with proper checklists, monitoring, and so forth. But right now, the people who are authorized to fly, the hobbyists, except for people who have paid attention, are some of the least trained people out there. Whereas the researchers, the educators, and so forth, are basically being told, you can't do it without all this exemption going on. We have a Section 333 that was approved the last couple of months. Any of you who've paid attention, that's the process that you need to go through to get the FAA to approve what's going on. They approved the off-the-shelf vehicles, the DJI, the 3DR. They did not approve a single custom vehicle that the researchers at the University of Michigan have built yet. Because they say, well, we haven't reviewed them yet. We don't know if they're safe. They don't trust the people who have designed and prepared them for flight. to say anything for themselves. Right? That's where we get into this notion of how scary it is to think that the whole policy regarding the air between here and that next building is governed by FAA, not the state of Michigan, not the city of Lansing, not the owners of these buildings. So let's get back to autonomy for a minute. So there's all kinds of applications, plus flight. I want to point to the Cessna at the top because one of the things that people may not realize is that general aviation actually needs the autonomy perhaps more than commercial transport because the safety statistics are not nearly as good. You have singly redundant systems, meaning if one component fails, it becomes more of an emergency than it does in the commercial jet. And you also have people flying the planes who often are weekend pilots. They're not people who fly every day for a living. So you end up with a combination of circumstances that makes more problems happen, which means that you need to have the kind of technology that allows them to be safer. Right, so this is a couple of things that I'm doing for research. And again, I want to reference the talk before me. One of the things that the bumper bowling example reminded me of in terms of artificial engagement was actually what we're doing with aerospace as well. There are two concepts. One is called geofencing. It's available in limited form on some of the existing multi-copter platforms that are sold. The notion of that is that you have coordinates of where you're supposed to fly, and the vehicle basically bounces off the walls to keep you into that arena, even if the pilot loses situational awareness. There's the keep out version of it, which was kind of prompted by incidents like at the White House, where people flew into the lawn with their multi-copters. So there, you would bounce off the walls, the artificial walls of the White House lawn. The research in this is really asking the question, how can we make it resilient, high integrity? You can pick one of many words. Because right now, to defeat the system, all you have to do is unplug the GPS antenna. And if you have an open source autopilot, all you have to do is comment out the geofence function. And so it's very easy to defeat. So you need to have embedded in these systems technology in the form of electronics and other components that the user would not find it easy to defeat to have these capabilities. And you furthermore need maps so that it's not the user entering coordinates, so that you have complete trust not only in the integrity of the user but also in their ability to enter numbers accurately, which is not I make mistakes when I type numbers in. I think most people do occasionally. So if you get a number wrong, then suddenly your geofence could be in a different state. So the other thing, which I think is a long-term question, is how do you actually have the ability for a system to maintain safety in even a manned aircraft by overriding bad decisions? So in the car, this would translate to don't let the car get out of its lane. Don't let it hit the car in front of it with adaptive cruise control. In the airplane, this would translate to don't let the plane, the commercial transport, fly out of its flight envelope. Don't let it stall, don't let it spin or get into an unusual attitude. It would also translate to don't let it run over the end of the runway. And it would translate ultimately to don't fly into buildings and mountains. Right? We know how to do that now, but our culture has not let us go there because we don't trust the autonomy. And the distinction between autonomy and automation is the autonomy can say no to the pilot or driver, whereas the automation just provides an assistive tool. Autonomy would say no, you should not fly into a mountain or the World Trade Center or the Pentagon, because that's never a good idea, no matter what the emergency. Right? And so there are a whole host of tools that we can bring into manned and unmanned aviation to make aviation truly safe. And then these policy questions become a little bit easier, because then we don't have to think that the rogue drone is going to take pictures of us in our bedrooms. That instead, it's going to be geofenced so that it doesn't get to go right outside your bedroom window unless you're the owner and you want to fly in your own yard. These technologies are not that far away. They're not somehow science fiction. They're things that we have the sensors and the software to do now, but we have to have the policy to go along with them. Right? So we have to have processes to certify and license small unmanned vehicles that can crash and not hurt anyone if they're over unpopulated areas. Those would be the low integrity vehicles. like my students want to fly as part of their research. We also need to have an acknowledgement that we need a high-integrity version of the small UAS. The high-integrity version would not crash into the crowd if it flies down an urban street, because it has the backup systems and the software to provide the level of autonomy that it needs to be safe. The most common systems failure in a small UAS is the communication link. Yet we're going down a path where we're calling these vehicles remotely piloted aircraft, knowing that by far the weakest system is the link, the communication link between the pilot and the aircraft. Where we should be going instead for these high-integrity vehicles is to move the autonomy onto the aircraft, to let it not fly through a building when it tries to return to base, to let it do something more than set down straight below when it gets a signal, maybe from a jammer, maybe from lost link, to flight terminate. There are better choices. We have the databases, we have the sensors, we have the software algorithms to make them, but we have to integrate them and let the flight testing happen and let them filter into the industry. The other thing is that we also have to acknowledge that these will be complex adaptive systems. Define that however you want, but the end is that these systems will need to learn, and they will need an alternative to the standard fault tree style analysis of risk, because they will be so large that we could never build this kind of standard analysis package to support them. And that is not so different than trusting a person, because we can't build a fault tree for a person either. All right, so many of you got the handout. This is kind of my summary of the policy issues. And I think because it's so close to one, I'm not going to talk about them too much, but the biggest issue right now in policy really is this kind of conflict between what remains kind of the sovereign property of the United States government to be regulated by the FAA and what should be going along with the property, whether it's a private or a public property holder. The logical thing, which just seems to be screaming out at me, I stare at this all the time, is to have high altitude airspace, say above 500 feet, and airspace around the airports like Detroit and Lansing and other places be absolutely controlled as it is now by the FAA. This makes a great deal of sense, and it protects the passengers who fly today. However, it also discourages the hobbyists and everybody else from flying there, because now you give them somewhere to go. Right now, they have nowhere to go. They might as well fly next to Detroit Metro, because we haven't told them that they can go out over a farm field and fly. We have in fact said, no, you can't fly anywhere. That doesn't work. We need drone parks. We need organizations, the communities, to come together and say, here's where it's okay for people to fly. Here's where it's not okay. Here's where the property owner needs to actually have authority to say yes or no. Right? If we're not careful, language that exists right now in the FAA Reauthorization Act for 2016 is going to make it hard for us to ever do that. Specifically, this is from yesterday in the Hill. Senator Nelson is trying to say that he hopes this package of amendments along with the rest of the Reauthorization Act will be approved very quickly because it's non-controversial. Well, maybe I don't agree with that quite so much. Here are two examples. The biggest one that I want to point your attention to, which is more general than universities, is Section 2152 on preemption. Now this is fine print, but you can look it up online as well. Here's what it says. Federal preemption. No state or political subdivision of a state may enact or enforce any law, regulation, or other provision having the force and effect of law relating to the design, manufacture, testing, licensing, registration, certification, operation, or maintenance of any unmanned aircraft system, including airspace, altitude, flight paths, etc. That right there is going to be a big deal. Because what that says is that there will at least be a legal fight between the state of Michigan, the community of Ann Arbor, or Lansing, or just a farmer who wants to fly over his crops. Because the FAA will say no one has authority. The reality is that that makes a lot of sense above 500 feet near airports because the FAA needs to protect that airspace and to be the sole authority for those areas, to protect everybody who uses those airports. But that is not the case everywhere else. So, there you go. Please read the handout if you... that you'll at least consider contacting your congresspeople. There actually, one more advertisement, there is a senator here in Lansing, Senator Pat Colbeck, who also happens to be an alum of the Aerospace Engineering Department of Michigan, who has introduced a couple of bills here in state legislature to try to protect the immediate reaches airspace. One of them, which I think is pretty straightforward, is basically looking at privately held property and saying that the landowner, consistent with the U.S. Supreme Court case, U.S. versus Cosby from 1946, has exclusive control and ownership of that very small immediate reaches layer of air over the property. Right? That would protect the airspace that we most need to kind of occupy and have control over it in conjunction with the land that we might own. There's also one for public property, but it's kind of a little more complicated because there you get liability issues and who has authority to do what. But please contact his office. I have a phone number if you're interested in talking with him.
Before I have one or two questions, to just say that these issues are sometimes in the future, they're sometimes in the now, and particularly with UAVs, they're very much in the now. The university itself struggled with a decision recently about potentially not necessarily meeting all the requirements of the FAA to fly a very small UAV very close to one of our own buildings to inspect a roof to increase the safety of that roof for our students. That was technically not legal because we didn't have all the permissions, but we could fly a 10,000-pound helicopter over that same roof the same distance away legally, and we hadn't ended up doing so, but you could see in that instance how it would be better if we could have just flown a small drone up there with a very small, maybe a higher risk of a very small impact of a failure instead of a low risk, high impact failure event with a manned helicopter. So these issues are real, they're now, they're in the future, they're 100 million miles away, and they're right in front of us in some cases with drones. So really appreciate your attention today, and any questions you have for the faculty or anybody, please.
So what is the millimort rate of a let's say, a under 100-pound drone versus a ladder?
So I'm so glad you asked. One of the papers that I wrote most recently is on thinking of zones of airspace that go along, not necessarily with all of the detailed zones of property, but somewhat in that flavor. So if you're flying over a large acreage, unpopulated farm, your risk is pretty much zero, unless you just happen to have someone asleep in the field. If you're flying over a city, it can be quite high. In fact, it scares me every time I see any sort of multicopter like the CNN one that I showed several times here flying over a crowd, because a quadcopter of that design is just not safe to fly over a crowd. So I don't know the exact figure, but I have seen enough quadcopters crash for various reasons to be quite confident in saying that that's not safe, especially with unducted propellers.
One of the questions in the first presentation relative to the sensor, how do you pick up snow, ice, that stuff, and then what's the comparable thing for your drones or planes?
Yeah, go ahead.
Sure, real quick. So it's an ongoing research question. I don't know if you saw, there's a video that came out in January of some snow testing at M City. We're able to see the snow, and we're able to localize within the with just the LiDAR sensor. We are also working on sort of sensor fusion techniques that enable us to sort of penetrate snow. So radar is not affected by snow. So combining, personally, I think that the answer is to combine different modalities of sensing that are not affected by various sort of interference methods.
Yeah, so for the planes, I mean, one of the reasons that pilots actually sit back in their seats and don't fly is when visibility drops so low, including heavy snow, that they can't actually see the runway. There is equipment available today, and there has been for a while, that allows you to have a zero visibility approach to a runway and touchdown. There, the big question is, has the runway been cleared enough that you're not going to skid off the runway? The other, for the small drones, at this point, the multicopters should have no business flying in the snow because the propellers are not prepared to deal with that.
With the comment, I have this new car with all these sensors, adaptive cruise control, and the salesman said, for God's sake, when you go to a car wash, turn the adaptive cruise control off, because it totally freaks out and will stop, because all the stuff is coming at it in the car wash.
Well, I think what you're pointing to is a big problem for both cars and planes, which is how can you make the sensor signals and the fusion of the data over the multiple sensors robust to conditions? And the examples that we're hearing right now, we know about. It's the things that are so rare that we couldn't anticipate them ever happening that we're going to have the most trouble with. In aviation, we have the luxury of having all of the accidents that have ever been investigated recorded and logged. And over the past 20 years or so, we even have black box data that's available online, the accident dockets, all of the black box data, for us to use as part of our research. And the auto companies are starting to get those kinds of data sets as well. So wouldn't it be nice if we could have autonomy that was prepared for every accident scenario that had ever been documented? We can do that.
One more question in the back.
How does it change a car to be autonomous? I mean, you talk to us about software a lot. Your person you're speaking for is from the East Department. Is this something you're bolting on to the Ford Fusion? You're adding 50 pounds of equipment, a bunch of sensors, or is it a fundamental change where a lot of the car is changing quite a bit?
So, which I have my presentation up still, but in the very beginning, the Ford Escape that I showed, that was basically a bolt-on kind of system. So all the sensors were bolted on. We had a third-party drive-by-wire, third-party company installed drive-by-wire. It was not a drive-by-wire system. And yeah, there's a lot of add-ons, and that did affect the dynamics of it a little bit. But with the 2014 Fusion, it was already drive-by-wire system, and so that was actually very helpful in being able to integrate more closely into the vehicle. And working with Ford enables us to do that. Now the sensors, yeah, they're an add-on package. It's an ongoing research question to sort of look at how can you best streamline those sensors, what's the minimum number of sensors you need, how can you integrate them more closely into the body of the car. But right now we're just trying to get the full data that we need.
Would a failure of a sensor disable the vehicle? Typically?
Well, I guess.
We could both answer that question. One of the things that happens is that the airplanes and the cars actually share a remarkably large subset of the sensors. If you do sensor fusion, meaning that you have diverse sources of information for the car or the plane, then you can be robust to the loss of any single type of data. Like he was talking about, maybe you lose LiDAR in a snowstorm, but then you have radar. The radar is not as good quality data, but it allows you to navigate safely, even though you're in a situation where one sensor wouldn't work.
Well, on behalf of the Wolverine Caucus, we could not have asked for a better talk today about autonomous vehicles. So I want to thank Assistant Vice President and as a show of our appreciation, I'd sure like to give you these gold Wolverine Caucus pins. So thank you again very, very, very much. And please, everyone, take a copy of Dr. Atkins' handout that's on the back table if you don't already have one. So again, if you'd like copies of the PowerPoint presentations that were presented today, we'll make those available to you. And as loyal members of the Wolverine Caucus, we look forward to seeing you again on Tuesday, September 20th. Please mark your calendars for Tuesday, September 20th, when we will be talking about elections 2016. So have a wonderful summer. Thank our speakers again, and we'll see you there.
side.